We can think of the mind and mental activity in terms of inputs and outputs. That's sort of the lens that we've been viewing it up to this point. That's sort of the computational framework that cognitive science assumes. There are inputs, some kind of process happens, some kind of computation takes place, and it produces some kind of output. And what we're interested in is we're interested in that middle part. What's happening between the input and the output? What process is taking place? What does that computation look like? But in some sense, it's kind of a black box. We can't really look inside the mind and see what's happening. We can't see the process unfolding. Even if we look into a brain, which we'll see later, we can have the technology now to look inside human brains and see what kind of activity is taking place and where. Even that may not tell us exactly what's happening in computational terms. It's like looking inside a beehive. You see a swarm of bees. What does it mean? So the mind in a lot of ways is a black box. And in the history of cognitive science, that was our starting point. The mind as a black box that could not be peered inside of. How can we figure out what's going on inside the black box if we can't look inside? How can we crack what's going on inside a human mind? So the history of cognitive science, in a lot of ways, is this ongoing effort to try to figure out what's going on inside that black box. One of the early attempts to try to make the study of the mind scientific and objective was behaviorism. John B. Watson, I think, put it best when he described it as a purely objective experimental branch of natural science. Its theoretical goal is the prediction and control of behavior. Introspection forms are not an essential part of its methods, nor is the scientific value of its data dependent upon the readiness with which they lend themselves to interpretation in terms of consciousness. So we've talked quite a bit about consciousness leading up to this. Consciousness raises a lot of questions that are extremely difficult to answer. And if we're trying to take the study of the mind and the study of thought and turn it into a scientific enterprise, move it into the realm of the objective and the observable, things like consciousness are not very amenable to that kind of approach. So the early behaviorists like John Watson, what they wanted to do is they wanted to move the study into a realm of the observable, move it into a realm where we can actually make direct observations. Make it scientific, make it rigorous, make it testable, make it falsifiable. John B. Watson kicked off the behaviorist craze when he wrote Psychology as the Behaviorist Views It. And it was dominant from the 1930s until the cognitive revolution in the 1960s. And it was influenced by a lot of work in animal psychology. The behaviorists thought psychology should be the study of behavior, not the inner workings of the mind. Mental states are inherently subjective and private and personal. We don't have direct access to them. We can't observe them. I don't know if I'm having similar mental states as another person because I can't directly access them. But the behaviorists thought psychology must be rigorous and objective. And to that end, its primary study should not be mental states. It should be behavior. Why? Because behavior is one thing that we can very directly observe and measure and control. So if we want a scientific study of the mind, we need to be able to make observations. Behaviorism focuses on what can be observed. Behavior. Introspection is too subjective and unscientific. Our hypotheses have to be falsifiable. And psychology should be as scientific as possible. That's why we're going to focus on the observable. That's why we're going to focus on behavior. There are a few flavors of behaviorism that developed over time. Methodological behaviorism said that science should focus on observable, measurable entities and behaviors. It didn't necessarily deny that internal mental states existed, just that that shouldn't really be the focus of the science. Radical behaviorism said, well, yes, internal mental states definitely exist, but they're not important, and they're not very explanatory, so we shouldn't care. Science should focus just on demonstrating relationships between behavior and environment, specifically. So this is the type of behaviorism championed by B.F. Skinner, who you're probably familiar with, the guy with the rats, the guy that did all those experiments with operant conditioning, training rats to respond to different kinds of stimuli and have different behaviors. Analytic behaviorism, weirdly, is a more radical version of behaviorism than radical behaviorism. This was championed by Ryle. Analytic behaviorists would say mental concepts only refer to behavioral tendencies. So we can't even talk about mental states at all, not in their own terms. Mental states don't exist the way that a cognitive scientist would think of them. Mental concepts are just ways of talking about behaviors. So even if we talk about mental states, say, oh, I'm hungry, or I'm in pain, or I'm thinking about something particular, that's just kind of a coded language to talk about the behaviors that result from those mental states. The mental states themselves aren't real. The only thing that's real is the behavior. This is a bit radical. So analytic behaviorism is a bit, in one sense, is a bit more radical than radical behaviorism, which isn't so radical. And methodological behaviorism is probably the least radical. Behaviorism was a dominant force in science of the mind for decades. But something changed, and it was a gradual change, starting from the 30s and the 40s all the way through to 1960s. So I want to walk now through a timeline of the cognitive revolution, see the major events, the milestones that led us to where we are now. In 1930, behaviorists Tolman and Hanzik conducted a series of experiments where they trained rats to navigate mazes. Tolman and Hanzik were behaviorists and they were doing behaviorist experiments, but this laid the groundwork for cognitive science because it showed that we could in fact make inferences about mental states. Claude Shannon, in 1948, creates information theory. He gives us the bit, the binary digit, as an atomic unit of information, framed in terms of entropy. How surprising is new information? In 1950, Alan Turing, the grandfather of modern computing, wrote Computing Machinery and Intelligence, where he specified a theoretical machine, which we now call a Turing machine, which forms the basis of all modern computing. George Miller, in 1956, writes The Magical Number 7, plus or minus 2. You may have heard of this. It's a quantification of the capacity of our working memories. In a series of behavioral tests, George Miller figured out exactly how much information the average person could hold in their working memory and for how long. And in 1957, Noam Chomsky, the father of modern linguistics, wrote Syntactic Structures, probably the most foundational and important text for modern linguistic theory. Together, all of these events constitute a sort of cognitive revolution, a transition from behaviorism of the past to cognitivism of the present. Instead of being stuck only talking about observable behaviors, now we can make inferences about mental states. We can make inferences about computation. We can quantify thought. Behaviorism views the mind as a passive device for mapping inputs to outputs. Cognitivism views the mind as an active device that processes and transforms input. And most importantly, the big change is that now we can make inferences about what we think is happening inside that black box where those dynamic processes are happening. But I want to go over a little more history about how we got here. Where did this start? So we can see in that timeline that there are several important events, several important milestones. But I want to talk in a little bit of depth about Tolman and his rats, because that's where this story really starts. Before Chomsky, before Turing, before Shannon, there was Tolman. Tolman was a behaviorist who assumed that all learning could be explained by conditioning, could be explained in behaviorist terms. And Tolman and his colleagues were testing the ability of rats to learn to navigate mazes. So I want to talk about these experiments and I want to think about what the results meant for behaviorism and what they mean for cognitive science. In his first experiment, Tolman trained rats to navigate a fairly complex maze. Because they were behaviorists, they were using reinforcement. The rats would navigate the maze and then they would get rewards if they navigated correctly. So if the rats got to the finish line, there would be some kind of food reward waiting for them. But they also wanted to test the effect that rewards had on learning. So not all of the rats were rewarded in the same way. There were 3 groups of rats. The first group was never rewarded. They wanted to see, could a rat learn to navigate a maze if it never got any rewards? Of course, the behaviorist would predict that these rats would learn nothing because all learning takes place through reinforcement. Without that critical component of reinforcement, the rats wouldn't learn anything. They had another group, the rats that were always rewarded. Every time they got to the end of the maze, they would get a food reward. And as behaviorists, they predicted that those rats should learn how to navigate the maze. Because of course, that's how learning works for a behaviorist. But they added another group. They did something interesting. They had a group of rats that didn't get any rewards for the first 10 days that they navigated the maze. So the rats were navigating the maze blindly for 10 days without getting any rewards. From the 11th day onward, suddenly the rats would be rewarded if they successfully navigated the maze. So we have three groups, one that's never rewarded, one that's always rewarded, and one that only is rewarded after a certain amount of time. So after the first 10 days, then they will be rewarded in the future. Now, as behaviorists, they predicted that this group, the rats shouldn't learn anything for those first 10 days. They're not being rewarded. There's no reinforcement, so there's no learning taking place. But from that 11th day onward, they should see the effects of learning begin. So whatever the rats learn, they should learn beginning on the 11th day and then improve from there. And I want to look now at the results to see what did they actually find, because it may be a little bit surprising. It was definitely a little bit surprising to them. So we can see in this graph the successive daily trials. That's every day that they would let the rat run in the maze. And we can see the number of errors that they made. As expected, the rats that were never rewarded didn't learn to navigate the maze particularly well. So starting in the first trial, the first day, the error rate is very high. It's almost 80%. Over time, the rats that aren't rewarded, their error rate goes down somewhat, but it doesn't ever really get below chance level. They're operating at about 50%. That's not very good. That's if you were navigating maybe randomly, you could expect a result like 50% errors. So these rats aren't particularly successful at navigating this maze. What about the rats that were always rewarded? Well, we can see their error rate starts at about the same place. It starts about 70 to 80%. But even starting from that first day, it's already dropping. And we see a linear trend. It drops over time. The longer they do the maze and the more they get rewarded, the better they are at navigating it. And that makes perfect sense from a behaviorist perspective. The more they're reinforced, the more they learn. Well, what about the rats that were in that other condition? They only got rewarded after the 10th day. What we see in that condition, of course, they start in the same place. They're making about 70 to 80% errors. But they seem to be performing about the same as the rats that never get rewarded for those first 10 days. So far, so good. This makes a lot of sense that they're performing at about the same level as the rats that don't get any rewards. Because, of course, they are not getting any rewards. But what happens at that 11th day? Suddenly there's a precipitous drop in error rate. Why? What does that mean? What that means is those rats suddenly and instantly became extremely proficient at navigating that maze. They did not start learning how to navigate the maze on the 11th day. They already knew how to navigate the maze. So there's something really kind of funny about this result to me. I always laugh when I look at this graph because what I see is I see a group of rats that were wandering around a maze aimlessly because they didn't have any reason to bother going to the end because there wasn't anything for them. Why bother completing the maze if I'm not going to get fed? They knew how to navigate the maze the whole time. They just didn't do it because they didn't care. Once the food was there, suddenly they become perfect because now they care. I think, wow, this always amuses me because really what it shows is that rats are a lot smarter than we thought. They're smart enough. The rats know if you're good at something, never do it for free. So this is an example of what they call latent learning. The learning took place without any conditioning, without any reinforcement. It just wasn't visible until the rewards started coming in. Behaviorists had assumed that all learning required stimulus plus response plus reinforcement. But Tolman found learning that was occurring without any reinforcement. It just wasn't evident until the reinforcement kicked in. The rats knew how to navigate the maze, they just didn't care. But what did the rats actually learn? For behaviorists, I think this question is kind of meaningless. their behavior changed so that they could successfully navigate the maze. What do you mean, what did they actually learn? But as a cognitive scientist, I want to know, how are they actually navigating? That's a computational problem. How are they doing it? How are they navigating the maze? What kind of algorithm are they using? For cognitive scientists, this is an extremely meaningful question. For behaviorists, this question is either uninteresting or impossible to answer. So now the question is this an answerable question? Is there a way that even a behaviorist like Tolman can find an answer to this question, what algorithm the rats are using their behaviorist methodology? So Tolman and his colleagues, they noticed that these rats were learning how to navigate the maze, but they wanted to know what exactly it was that the rats were learning. This is fundamentally a question about mental representations and algorithms. Tolman thought there were two possibilities. Either the rats were learning something called response learning, where they learned by remembering a specific sequence of movements, like go straight, turn left, turn right, etc. Or maybe they were learning according to place learning. That's learning by remembering the spatial layout of the maze. So if we think about the different algorithms that are possible that could get you to this output state of successfully navigating a maze, right? There's more than one way to successfully navigate a maze. You might navigate the maze by just remembering to go left or right in a very specific sequence. But there's another way of solving a maze. You might solve a maze by remembering where everything goes, having a mental map, remembering what the spatial layout is and where the exit is relative to the entrance. And by keeping that map in your mind and updating where you are in relation to those points, you might be able to successfully navigate to the exit. Those are really different algorithms that entail really different mental representations. The exact thing that behaviorists think we can't know. So if they can figure that out, then they will have proved that not only is it possible to look inside the black box, but they will have done so. I love this experiment because of its simplicity. It is a deceptively simple experiment. Forget the complex maze with all those corridors and twists and turns. This is not even a maze that we would think of in the conventional sense. It's only an intersection of two hallways. So there's a cross-shaped maze, and the rats will be placed at an entrance, and all they have to do is remember whether they should turn left or right to get their food. That's it. This is the easiest possible maze to navigate in the world. Should be pretty straightforward to figure out. Do I need to turn left or right? Which way am I going? Where's the food? There's only one intersection. There were two groups of rats in this study. For the first group of rats, the food was always located in the same place. That is, it was like always on the east side of the maze. And they would sometimes place the rat on the south side, and the rat would have to turn right to get to the food. Sometimes they would place the rat on the north side of the maze, and then the rat would have to turn left to get to the food. So this is important because this means that the only viable way for the rat to solve the maze is to remember the layout of the maze and then be able to place themselves on a mental map, to position themselves on that map relative to the exit. You won't be able to solve this by always remembering to go left or go right. You have to know where everything is and know where you are in relation to everything else. You need a map. Group 2 is the response learning group. This group, the rat would always be shifted from the north side to the south side, but the food was also shifting from the east side to the west side, so that the rat would always turn right. In some way, this is maybe a lot easier to do, right? You just have to remember, turn right. That's pretty straightforward. The food is always going to be one right turn away, no matter where I start from or where it is. So in order for a rat to learn how to solve this version of the problem, they have to remember to turn right. They can't just create a mental map and map themselves in relation to the endpoint, because they don't know where the endpoint is. The endpoint is always changing. The only thing that's constant is that they always have to turn right. So we have two groups of rats. One has to use response learning. The other has to use place learning. Those are the only viable algorithms to solve the mazes in their respective conditions. So if we look at the results, how well these rats learn to navigate these mazes, we should be able to tell what kind of algorithm each group is using. If each group is successful, then that'll tell us that they are using that specific algorithm that is required to successfully navigate that maze. If they don't do so well, then that might tell us that they're not using that algorithm, that maybe they're trying to solve it in a different way. So group 1 has to do place learning, and group 2 has to do response learning. If the rats are naturally good at place learning, if they naturally create mental maps, then group 1 should learn a lot quicker than group 2. But if rats are good at response learning, if that's their natural algorithm that they use to solve these mazes, then group 2 should learn a lot quicker than group 1. I think these results speak for themselves. The rats in group 1, the place learning rats, their error rate goes down to 0 by the 10th trial. Whereas the response learning rats are kind of all over the place. Their error rate never goes all the way to 0. They never successfully learn how to navigate the maze, not perfectly, not the way that the place learning rats have learned perfectly. So there's a big difference here between these two groups. The rats that are using mental maps are learning the maze perfectly by the 10th day. The rats that have to remember to turn right, they never reach that perfect level of performance. That tells us that these rats do have a preference for one type of learning over the other. And it tells us something even more than that. It tells us the exact kind of mental representation that these rats are using when they're trying to solve this problem of navigating this maze. It tells us what algorithm they're using to get to that output state. So rats are good at place learning, but they're bad at response learning. So what? Why is this interesting? Well, we've just done something that the behaviorists thought was impossible. We made an inference about a mental representation based on observable behaviors. These rats are generating a mental representation of the maze. They're generating a representation of the spatial layout. There's just no other way to explain this. It has to be a mental representation. So Tolman's rat experiments show clear evidence of mental representations. They show clear evidence of unreinforced learning, of latent learning. They show clear evidence of specific algorithms being used by rats to navigate mazes. And just with these few results, behaviorism is now in trouble, and the cognitive revolution is in full swing. Now we know we can make inferences about internal mental processes and mental representations that the behaviorists assumed were off limits or unobservable or maybe even didn't exist at all. Okay, I just want to sum up the key concepts from this lecture. We talked about behaviorism in the context of the history of cognitive science. Different types of behaviorism, methodological, analytical, radical, the different commitments that each of those viewpoints entails. We talked about latent learning, the fact that these rats can learn to navigate mazes even when they weren't being reinforced. The learning only became apparent later, after the reinforcements kicked in. We learned that rats are doing place learning. They are navigating via mental maps. They're creating mental representations that encode the layout of mazes inside their own minds. They are not doing response learning, memorizing how to navigate mazes by remembering which direction to turn, remembering a very specific sequence of behaviors. And we talked about the concept of mental maps, the fact that a rat could create a mental representation that encodes that spatial layout. And that this represents the first time that cognitive scientists were able to penetrate into the black box and see the inner workings, look at a mental representation, look at an algorithm. And that informed everything that cognitive science has done since then.